Hello, everyone. So welcome to ITS 365. All right. Welcome. So we're currently recording. Here we are. Okay. So this week, as I said, we've completed our very first machine learning section, which was the KNN algorithm, right? And then we started our discussion of recommender systems and a technique called singular value decomposition on the 7th of February. Today is the 9th, so we will just continue our discussion. All right, so I already went over the theory and I gave you an example, so hopefully that made sense. You can look at the video, which should be on YouTube if you have, kind of reinforce your knowledge there. And today we're just going to spend, like a workshop, just go over the code, kind of get it to work. Now, this homework, I usually like to think of it as a mini project. Okay, so I want you guys to, kind of have fun with it, but do something very real. So you're going to do a recommender system, right? And we're going to take some time for you to demo it. So that means you'll have, what I want is some functionality where I can, rate a few products, and then it should recommend something, right? And then, and then the success would be if I'm like, oh yeah, I would buy it, right? So your grade depends on that. But so that's the idea, right? So so recommend, singular value decomposition. So I went over this theory. I'm not gonna go over the theory anymore. So with the example and everything, it should have been clear. And so instead, what we're gonna do today is just continue with the code. So I'm gonna open up the Jupyter notebook. I'll need to share that, of course. All right, so let me share that on the screen here. Okay. And also, I guess before I forget, in the calendar, exam 1, right? So we've marked this for February 14th, that Monday. So if you guys want, we don't have to come to class, given that it's an exam electronic, or do you want to take the exam in class? It's up to you. What about you guys? It doesn't matter about, you can take it anywhere. I mean, so let's see what Lenny says. Yeah, taking it at home would be nice, right? So so let's do that. So the exam, you can expect it to be, you can take it wherever you want, really. Yeah. So obviously it'll be an exam that mixes up maybe some essay type questions with problems that you have to solve. So it won't be, it'll be a little bit interesting there. Okay. So that's the idea. So you can expect the exam on Brightspace at 12 o'clock, and I'll give you the 2 hours that the Brightspace allocates. And so you'll have to submit the exam though before it closes. So I strongly recommend that you submit once, like 10 minutes before, just in case. And then you can submit again if you'd like. Please do not email the exams 3 hours later. Okay, so definitely no, don't do it. Yes, I always set everything to be unlimited. Yes, so you can always submit, although please don't submit 7 times, right? That's just meant for you to have some flexibility. I'd rather you submit something than not, I have a bigger problem if you don't give me your exam. And so, yeah, so please submit your exam. You can expect between 5 and 10 problems. Okay, there will be a little bit different. You'll have to think. Again, I'm not looking for perfection in your code. just that your logic is correct. Okay, so I may give you a problem that we've never talked about, and I may just ask you to describe the pipeline. You guys see that? Of machine learning. All right, so it'll cover everything that we've discussed from the beginning all the way to today, basically. So today we're going to continue our code with singular value decomposition. So let's switch over to here. Okay, and then I'm going to go into the desktop, ITS 365, and then I believe we were here. Okay, so we started looking at this. If I run it, right, it runs perfectly. So today we're going to just advance a little bit more with the code. And then at the end of the day, you should be able to implement this on your own. Okay. So, let's just do a quick recap. We did import NumPy as an NP, pandas, of course, so the two libraries that we're using for manipulating the data. We're using the movie lens dataset. Okay, so we use the movie lens data. So we read in a file. So in this case, we're reading in ratings. Remember, this has user IDs, movie IDs, and the rating itself. So those are the three columns that we need. Okay, there's about 100,000 different ratings in there. And then we just need to load that as either users to movies or movies to users. Doesn't really matter, but we need to do that basically. Okay, so here we have a way of getting the column, so that user ID, and we've also gotten the unique values. Okay, so we know that we have about 9,724 by 610. So 610 users, 974. Remember, I said that the movies actually go from ID 1 to 170,000, but there's missing IDs. So I think it might go from 168,000 one ID to 170,000 another ID. So notice the big gap. Now we can't create a matrix like that because that would be what is called a sparse matrix, too many zeros in it, but those zeros still count in memory. The computer still just puts zeros in memory. So that's the same as putting numbers. So it's going to become almost impossible to solve something that big. So what we need to do is we need to find a mapping where we create IDs that are 9,000 IDs, but they are mapped to the real ones. Do you guys understand that? So like 9,723 would be 168,000 ID, but then 9,724 would be the 170,000 ID. You see that? So that mapping solves the problem for the dimensionality issue. All right, so that's the idea. All right, we also printed the data head, so we already looked at that. Here we have the ratings file, right, in data ratings, and then we also got the movies. Remember that we have movie IDs, and so once we get a movie ID, we want to recommend an actual movie, the name. So we want to say The Matrix, or Saving Private Ryan, or something like that. And so we need to have this has those actual IDs to names of movies. All right, so then the next step is to create a NumPy array of zeros, a matrix basically. And notice here that we did it of shape 9,724 by 610. All right, and the values are uint because they are ratings, so they are integers from 0 to 5, right? So no float. So we're going to call that ratings matrix. That's the name of it. And then here I just printed out the shape, as you can see. So there I have, this is where we left off. Okay, so now we're going to proceed and do a little bit let's think about what we're going to do. So in data ratings, now we have all the ratings, but we want to extract each individual one of the columns, right? So we want to extract the movie, well, the actual rating, the movie ID, and the user ID. So we're going to do that because pandas is, it's a really nice frame, right? So if you notice, if I do this one again, you can see that pandas grabs the label, user ID, movie ID, rating. So basically, these are the things we can reference these columns by this name, right? And then extract the whole column, all 100,000 of each. And we're going to have them basically available to us in our own data structures. All right, so let's go ahead then and do that. So I'm going to create ratings array, let's call it. Okay, ratings array. We're also going to create, let's call it movie IDs. Movie IDs array. And also user IDs. Okay. All right, so then we're going to grab this individually from the ratings, from the data ratings frame, data frame. And now we're just going to say dot rating because that's the name of it. Okay, so we grab rating. And then once we grab the column is still an object. So we still need to tell it, okay, but from that object, I want the actual values. Okay, so that's what I'm doing. Then I'm going to do the next one, which is, same thing, data ratings dot. And now it's going to be movie ID dot values. And then finally, data ratings dot user ID dot values. Okay, so this has the data that we need. So let's just run it, make sure there are no typos, so it works. You can print it out if you do print, and then length of this. So you do len, and then you do ratings. Ratings array, right? And we do run, you'll see it's 100,000. So each one should be 100,000. We've got the data in there. You can also just print the actual data itself. You'll see you have the 5s and the 4s. See that? This gives you a shortened version of it for you to view. All right, once we have this, the next step is we want to create these reverse dictionaries. All right, so these reverse dictionaries are actually very convenient. This is done a lot in machine learning. You always create these like mappings, right, of the IDs, the real IDs to the, let's call them the reference IDs. You guys see that? So the real ID is the movie 170,000, but the reference ID is only 9,724. The mapping, yes, so that we can keep our matrix smaller. Otherwise, you'd never be able to do this homework. I promise you. With 170,000, none of your computers will. All right, so that's the issue. So we have to be efficient in that regard. So let's do this. We're going to create. Let's do it first. So we're going to need this for users. We probably don't need it, right? Because I looked at the data. There weren't any missing. So technically, we didn't have to do it, but let's do it for both. But definitely for movies, we have to do it. That's a certainty. So then I'm doing movies here, right? And so movies underscore unique. And then I'm going to call it dictionary. And then here we're going to specify the type of mapping. So I'm going to say real, or sorry, I'm going to say in this one, reference to real. Okay. So that way, what's great about this is we're going to make the dictionary, the same dictionary, but with the things inverted. So one is going to be ref to real, the other one's real to ref. The convenience of that is that if you have a ref, just look it up and you get the real. If you have a real, just look it up in the other one and you get the ref. So it just speeds up things quite considerably because dictionaries are actually really fast in Python. They're a hash table, but if you do it in this format. So it just makes sense. You guys see that? So it's like we're duplicating, and you might say, why don't you just use one and look at the other way around? Well, this just makes it faster. Again, speed, right? Speed up. So reference to real then will be the dictionary here, so curly bracket. Then we do the other one, so that's going to be movies. And then I think the way that I wrote it is uniques. So then movies, uniques. And then this is also a dictionary, but this is the opposite. This is real to ref. And then this is going to be curly bracket there. Okay, so now that we have this, now from the movie IDs array, which is this one, right? Here we have 170,000 movie IDs, but we just want the unique values, okay? So then we're going to create another one, just call another array, call it movies uniques. Movies uniques. Call numpy, so np, right? And then now we call the function unique. Right? Unique there. And we just plug in here. Where is it? Here, up here. Movies, movie IDs array. Okay, so that we can actually get the IDs that we need. Right, and then once we do this, then we're just going to populate the dictionaries so that we now have them available going forward. All right, so we're going to use a really nice function in Python called the enumerate function. It's learned. It's a very helpful function that solves a lot of problems. So we're going to do, for instance, for IDX res in enumerate, and then you just enumerate from movies uniques. So movies, I'm just going to copy this one. Just like that. Okay, so what this function does is it's going to enumerate all the unique movies in here, which are about 9,724. But the enumerate function returns two things, returns a tuple, two things. And what's convenient about it, it returns the index and also the value. Do you see that? So what's great about that is you don't have to create like an extra I variable and then increment it I++ and all that to keep like a counter. You don't have to. It just does it automatically. So basically your index is I. So the index that's going to be from 1 to 9,724 is the I. And then the rest will be the actual 170,000 ID, the real ID. Okay, so this one becomes the reference. This one becomes the real. Is this clear for everyone, guys? Any questions? No? All right, so now that I have this, now I just proceed to populate the dictionary. So I'm going to grab these two dictionaries, right? I'm just going to copy them. Just like that. So now I need to, oops. Oh. Get rid of this. We don't need to declare the dictionaries again. So now what we need is something like this, right? So we need to define an ID and define the actual value, but they're just going to be inverted. So let's just think of the logic that we're following. Ref to real means that the reference is the ID and the real is the actual value, right? So that means that this should be IDX, and then this should be res. The other way around, real to ref, means that res should be in here and IDX should be there. That's all we did. But again, this is going to help us because whenever we have a reference, we just go into this one and we get the real immediately, like extremely fast and efficiently. If we have a real value and we for some reason need the reference, we use the other dictionary. Got it? All right, so that's good. Now, although we don't have to do it for users, let's go ahead and do that same thing for users. Pretty much the same logic, so I'm just going to copy and paste it. Okay, so obviously I'm going to change the name here to users. And then this array will be user IDs array. Okay. And then still enumerate, still use IDX and res. This is going to be users uniques. Okay. And then the dictionaries are going to be user uniques. So we just have to users. Okay, so now that we have that, we have res and IDX, right? That should be the exact same logic. You guys see that they're consistent, right? You don't see anything that I missed. All right, so let's go ahead and save it first of all. Run it. Okay, good, no errors. So that means the dictionaries were probably created correctly and we have them available. So now you have a quick way of building your matrix. So remember, now you have the ratings matrix, right? This is going to be the thing that you're going to apply singular value decomposition to, okay? Remember, we would take an X and then we apply the singular value decomposition and then we get three matrices, right? Where it's gonna now, instead of being movies to users, it'll be movies to concepts, that's one. And then the other one is concepts to users. You guys see that? And it allows us then to group things in some way. We won't know. In particular for this, it makes sense, right? It'll be, you know, this. But let's say you guys, that example we discussed in class of the ads, right? Getting ads. You don't know what the ads will be, right? It might be sporty ads, and it might be probably car ads, right? You know, that kind of thing. So you won't know what they are, but it will create some, and then it'll tell you which components are the best ones, which is really what's important. All right, so, all right, so now that we have this our dictionary here, you know, we need to proceed to create or populate the ratings matrix, right? So we need to populate this one with the data itself. Okay, so we can just think about how to do that. So now if you guys want, we can print out also one of the dictionaries, kind of view it. I'm going to say print movies uniques, and then dictionary ref real. Yep. All right, so let's run that one. See, there's the dictionary. It's got the mappings as we discussed. So see that? I did the movies. If you look here, there's already a spread. The reference is 243, but the real one is already 281. You see that? It's going to become wider. If you go to the end, notice that 9723 is actually 193,600. Make sense? Let's just comment this out though, because we don't want that to take up too much space. Let's run it again. And there we have it. So now, let's do the next thing, which is print it out. So now what we want to do is we want to populate the data, right? So we want to populate ratings matrix. So some kind of for loop. For dot. We'll have to think about that one. 1, 2, 3, 4, and then we're populating ratings matrix. Okay. This is of course a two-dimensional matrix, so there's indices here that we have to figure out, right? And then we are going to definitely provide we're going to provide the value is stored. Where's the value stored? The rating, I mean, where are the ratings located? Ratings array, right? So they're located there. So we're going to have to grab this from ratings array somehow. So from ratings array, and that's just one thing. So probably the easiest thing might be to just go through ratings array, right? And grab all the ratings from there. So I'm going to do, and we can think about it if this makes sense. So for I in range, okay, and then we need to know, so there's 100,000 or so ratings. So then let's do length, right? Length of ratings array. So that allows us to iterate. So now we're iterating through every single one, right? Now, if you remember, let's go to the whiteboard here. Okay, so if we go to the whiteboard, we have the ratings array, the movies array, and the users array, right? We extracted these with pandas, and we have 1, 2, 3, ... all the way to about 100,000, right? So currently we are iterating through ratings array, right? We said length of ratings array, so we know there's 100,000, but they all, so for every one of the ratings, there's a matching movie and there's a matching user, right? So like if I'm at 4, I4, in each one of the lists, there's the 4, the rating. For that, the corresponding movie ID, which, let's say it was 3, and the corresponding user, which will say 17. You guys see that? So we can treat the 3 arrays, because they're all of the same size, right? When we're iterating through one, just by index, we can grab the corresponding values from each one. You guys see that? Is that clear for everyone? So that's something to think about, right? So that we might be able to use that. So then we have, this is in ratings array, right? So now I go back to the code. So I'm talking about these 3 ratings array. All 3 go to 100,000. So when I grab rating 3, I can grab movie IDs 3 and user IDs 3, and therefore I have the rating, the user, and the movie. And then I just have to plot that. I can use those values as the indices in the matrix. Do you see that? So for instance, let's say that I'm at rating 17, right? So I grab that, that's rating 3, but it said that the user was user 88, and it says that movie was movie 2000. Well, then I'm going to go to indices 2000, 88, and plug in the rating. You guys understand? Is that clear for everyone? Now, the only thing is we're not actually using the real movie IDs. We're going to use what? The mapped ID from the dictionary, because we don't want the matrix to be too big. Got it? So that's basically all it is. So we can do this here, right? So now we're going to figure out, first of all, we want to get the reference. Let's call it, so let's actually say, so we've got ratings. Oh, this is a type. It should be I. And then plug in I here, right? We just grab that rating. But we also need the corresponding movie ID. So we're going to go to user IDs, right? So from user IDs array, and also we grab I. You see that? So I grab that one. And then I'm going to do the same for movie IDs. Movie IDs array. Okay. And we're also going to grab I. So I've got both of them. And if I, and then, so now I need these. So I could just call it U and M. And then in theory, I would just be able to plug these in. We said that movies were going to be the rows and then users the columns, right? So that was 9,000 by 600. So then we would just plug in M. Oops, sorry. Does this make sense, guys? However, if we did just this, that M would be 170,000 for some movies, right? It will be the real. So then what we need to do is call the dictionaries and find a mapping. Okay, so now I'm going to say, let's call it ref U. And let's call it ref M. And then these are going to be a result of calling the dictionary. So now I'm going to call users. So users uniques. So let's just copy the dictionary. So that here I need the ref given the real, right? So I need the ref given the real. So that's this one. You guys understand? I get movie 170,000. I need the equivalent reference ID 9,724. So then I'm going to do here movies uniques dictionary real to ref, and I'm going to plug in here M. Oh, wait, this should be at the bottom. Well, actually, let's just do users. All right, so users, uniques, dictionary, real to ref for both, because we've got the real and we just need the reference. So then we plug in here U actually, and then here we would plug in M. Any questions? Does this make sense?
I do have a quick question. Is there any reason we would use using M for? Never mind, I see it now. I thought you had M for users were, and then you had U where M were, but I was wrong.
Okay. Yeah. So here we just want the reference U and M, not the real U and M, because of the dimension. So then here, all that remains that we have to change these So now this is going to be reference M, and then this is going to be reference U. Okay. So now that's it. We're done. We've got the array, the matrix, and that should work. So let's go ahead now and save it and run it. Oh, okay, now if we want to visualize it, we can print ratings matrix. Let's save it and run it. And you can see there, it's got values, right? So that should have done, should have completed the task. And now we have our matrix. So now we can apply singular value decomposition to it. Okay, so that's the next step. Now there's a few additional steps that we can come back to. But let's for now do so let's think. So the next step would be to think about singular value decomposition. So there is an option in NumPy to do that. So I'm going to call NP lin ALG. So this stands for linear algebra dot SVD. And then we just plug in our ratings matrix. So ratings matrix. And then this should produce U, comma, S, comma, V, which are the three matrices that we have talked about in class on Monday that basically indicates the decomposition. Okay, so let's see if this will run. Okay, so it ran, you can see that there. Now we can proceed to print out the shapes of these. So I'm going to do print. Now you can always improve on this by doing a few additional operations. Okay, just like that. So we have U, S, and V, and we're going to print out the shapes. Oh, there, yeah. So as you can see, if you think about it, it created square matrices. You see that? So basically, it's got the 9,000, and then it created 9,000 for the other one, but not all, obviously, that not all 9,000 are going to be useful. In fact, only the first few would be useful. You guys see that? So that's the basic idea here. And remember, this is also an implementation of the math. So the math was something, theoretically, and then there's people that implement these algorithms. So they don't cover everything, right? So they have little things. So now we have to work with this. But basically, this is the idea. The same for the users here. This is now mapped, okay? So what we might want to try to do is take a look at some of the values. So that would be the next step. Let's try and take a look at some of this. Okay, so let's try to look at something here. So let's take a look at U. We're going to slice out some information. So U would be, let's say, Usually the first few components would be the most important, right? So in this case, these are the movies, because there's 9,000 of them. So I'm going to say from beginning to about 10. And then also I'm going to want the first, let's say, 5 components. Okay. You guys understand what I'm saying here, right? So remember that the matrix let's go over here. So we have our matrix 9,740, let's say, by 610. It decomposes it into 3. This one is going to be 9,740, and it will be, it came out by 940, but really, it's not all of them, right, that are important. So really what I'm doing here is slicing just, let's say, that little piece. You see that? So that I can take a look at the information in it. And then this should be the principal components of the information. So you can take a look at that. So now we go back to the code. And I already did the slicing, so let's go ahead and run it. Takes a while because the algorithm SVD is actually thinking, right? So imagine if it was 170,000, it would have taken longer to do that. But see, it's pretty fast. And here they are. Do you see that? So it's saying that these movies, whatever they are negatively correlated here, positively correlated here, negative here. Here, you start to see some confusion already. Do you see that? But the first one seemed to have been a little bit more on the dot. So maybe this was sci-fi, but then these movies were romance. Do you see that? And then maybe these, because this is romance and this is romance. You know, and that's where you have this idea now. Okay, so that's really what happens here. Okay, so now let's think. So now, what do we want to do now? So I guess what remains now, we might do some additional things to improve the efficiency. We can also look at the other ones. Obviously, we can take a look at S. Take a look at S. Oops. Too many indices for, oh yeah, it only has, so it's a vector actually, right? So then let's take this out. So you can see it's almost giving you just like the diagonal here. So let's do 20, no, 20. If you look at this data in this vector, can you see a pattern? What's the pattern? Yeah, it's high to low, right? It's going down. Exactly. So that's kind of the weights of the vector. So you can see some are more, the first ones are more important than the rest. Okay. So that's the idea. We can do it all the way to 610. Let's do it 609. Okay. So now I'm gonna do. And if we look at all the data, towards the end, these components of the produced matrices are not as useful. Okay, so that's kind of the intuition there. So let's go ahead and comment this out now. So now what remains is, as I said, we can do some improvements, but like normalizing the data, etc. Those are always recommended steps. But so you basically have what you wanted, right? So you have the data, the ratings data, and then now you're able to decompose it into these three, U, S, and V. So this is actually how Netflix had something called the Netflix Challenge. And basically they were going to give $1 million to whomever came up with the best solution. The problem for them was that it's Netflix. So think about how many users does Netflix have? Millions, right? Let's say they have 100 million. And then how many movies are there? Thousands, right? Let's say, could there be 1 million movies? I don't know. But there's a lot. And so their problem was they can't do what we did, right? Of making the matrix smaller. So if they have 100 million users and they want to use all that information, presents a bigger challenge, right? So there's something called robust SVD or robust PCA, which are even more advanced algorithms that handle that kind of thing, where it's an incredibly large matrix, but that's more complex. So just be aware of that. So the matrix challenge was basically using this idea, but solving the real problem of how big the matrix was, because they wanted to use all the data, right? So there's a few, but anyway, that's just a comment. So this is, simple for our purposes. So then now what remains is almost like we want to talk about the term project, right? So what do you want to do in the term project? So, what is our goal? So what is the goal of the project? Exactly. But not using movies, right? So your challenge will be, and I suggest you start doing that as soon as possible, you need to find your own data. Try to find data in this format, right? So that you can just follow the code, but you get the basic idea of what we did and the format that the data needs to be in. So then you need to find some data, and then you're going to make recommendations. So how do we make recommendations? We're going to make recommendations based on, I pick a few movies, let's say, or a few products, and then you have to use USV to recommend others, right? So you'll definitely have to compute this, but then comes the part where you kind of have to figure out what you're going to do, okay? Now, another way of thinking about this is as follows. You think about it. So do you remember that all semester we've been saying that, we create vector spaces, Rn, let's say the example of R3, right? R3 is that, and that. And so that's F1, F2, F3. So this is like income, age, height, right? And then you put people in here. So then when you have, let's say, 4 people there, and then you have 3 people there, and then you have an extra person that comes in, let's say star, which one, what would you say this person is more on the purple side or the green side? Purple, right? Why? Because it's closer. That was KNN. Remember the Euclidean distance? Believe it or not, we can do the same with singular value decomposition. It might sound Not very intuitive, but actually we can do the same. So how can we do the same? So I'm saying calculate a similarity. That's one thing that we can do. Well, how do we do that? Think about it. Now we have, initially we had all the movies and all the users, right? But now we have these matrices where we have all the movies here, 9,740 movies. And then now I've created these concepts, or let's call them principal components, or whatever we want to call them, all the way to 9,740. But as it has been established, not all of them are good, right? So only really the first ones. So really, you could just make a choice that I'm just going to pick the first 10. That's it. And I'm going to slice that out as I was doing. You see that? So I slice out until 10, right? So then what do I have? This U matrix, when I slice it out, so I do what? All of them here, right? And then I do from beginning to 10. Do you guys understand what I'm doing here? Okay, so now I have that. If you think about it, in the analogy of the previous one that we did this spacing, well, now it just so happens that that's also a vector space. U, the sliced U, is what? Is 9,740 by 10, which basically means it's a matrix just like any other matrix, where we have movies here, 9,740, yeah? And then this goes from P1, P2, all the way to P10. So really, every movie is now being represented as these 10 principal components, which are similar to saying being represented by 10 features. Do you guys see that? Age, height, weight, the 3 is equivalent to this. So then this itself is a vector space, right? So this is a vector space of how many dimensions? How many dimensions does this vector, this X, how many dimensions does it represent as a vector space? 10, very good, 10. Now I can only draw 3 because humans were limited to 3 dimensions, but mathematically these are, imagine that they are perpendicular all to each other. And what that means mathematically is they're independent. You see that? If they were not like this, if they were like this, then there's some correlation between them. You don't want that. If they're like this, they're totally independent. And you want that, right? Because what's the point of having a feature that is income and then another one that is number of houses with swimming pools that you have? You know what I mean? It's going to correlate. The richer you are, the more swimming pools you're probably going to have, right? So, so that's the idea. So you don't want correlated features because that increases your vector space. That just doesn't work. So anyway, so now you have P1, P2, P3, P4, ... all the way to P10. Do you see that? So every one of these movies is now represented in this vector space. Do you see that? Exactly like the other one. Exactly. The number of dimensions does not matter. It's a space, therefore you can calculate distances between the points. So what are the points now in this vector space, which is R10? What are the points in it? Each movie, exactly. Each movie is here. Do you see that? Do you see the beauty of this? And now I grab another one, blue. Recommend. Right? Because if I pick, let's say that I'm, you know, as I said to you guys, I'm going to pick this one and that one. Well, then just recommend any of those, right? Don't recommend this one when you have these here. Does this make sense? It's like those chairs over there are in the space and they're sci-fi, and those over there are like romance. And I say I like romance movies, so then recommend those because they're closer. That's it. That's a way of doing this pretty nicely. Pretty easy. And notice that I reduced the dimensionality of the space to 10 dimensions. I have until 600, but probably 600 is not necessary. Try it with just 10 and see if it's good, right? And then and just play with it. You know, eventually you'll find an optimal value, like every day, right? You use a different one. You say, today I'm going to recommend with 10. See how many people watch the movies. Then the next day, no, today I'm going to try 20. Eventually, you'll say, well, you know what? When we do 40, people have a tendency our revenue goes up because you're selling movies. And that's how you learn. You guys understand? So that's basically it. So we've already done Euclidean distance. You already know how to do this by hand, right? What do you need? Slice it. We already, that's it. Slice this matrix, right? That's a vector space. And then now it's all 9,000 movies. I'll pick some, and then you would just want to find the most similar ones. How do you do that? The best way probably to do that is to just calculate what is called a similarity matrix. So in a similarity matrix, what you do is you have 9,000 movies over here, and now you have 9,000 movies over here. Each movie then, let's say movie 7 is, or actually it's 7,000 probably. So let's say 700. It's going to be compared to all other movies. You see that? And then you'll have the similarity score here, which is the Euclidean distance. Does this make sense? And then now you have the distance, a matrix of distances, and you can just really quickly find the thing that you want. Because you can just sort them, right? Think about it. You take this movie. So I rated this, right? And so now I grab this with all the distances to all the other movies. And what do I do with this array? Just sort it. And then when I've sorted it, I pick the top 10 that aren't that movie. Because obviously you're also going to compare to 700. And that distance will be 0 because it's the same point in the vector space. So ignore that one, but you do that, and then now you should have the top 10 movies to recommend. Is this clear, guys? We'll go over the code, but I just want to make sure that the concept makes sense. All right, good. So it seems I'm not hearing any questions. No questions on the chat either. Let's see.
So we have a total, real quick. So we have a total of 9,740 movies.
Yes.
All right. So
what's your question?
Each one of those numbers going down, I'm just making sure I'm understanding it. Mm-hmm. So each one of the numbers on the left are samples, is a different movie, and the different little criteria is on top features.
You mean this one here, or which one?
The 700.
Yeah, the 700 is a movie. It's an action. So this is the similarity matrix. This is a new matrix called the similarity matrix. Okay. A lot of machine learning is this. A lot of it. Just so much of it. Like the solution to everything. Create a vector space, take the distance. That's why I started with KNN. Because even singular value decomposition is just a step that then can be used with other things. So what I do here with the similarity matrix is, as I said, my goal will be to calculate the distance between all the movies. So to do that, I create a matrix that is 9,740 by 9,740. It's squared. And then now I can tell the distance between 702, that might be 50. And then the distance between 700 and 9,740, that might be 3. So obviously then this is a closer movie, so that's the one I would pick if you like 700. Do you understand?
I do now, thank you.
Okay. All right, so hopefully that concept made sense. So let's think then about, now, how do you calculate that efficiency, right? So, you could do a for loop. But what did I say about for loops? Slow, too slow. If you do it, if you're the Netflix price and you have 100 million users, should you use a for loop? Probably not, right? It's just not going to work. So this is where, again, linear algebra comes in, because we can just do what is called a matrix multiplication. We multiply, and then we'll be able to really quickly get the distances. Okay, so I'll just give you this, but now let's go back to our code and let's just kind of work through it, right? So what I want you guys to do, the goal is going to be to recommend similar moves, right? And there's several things that we can get out of SVD, but right now we're going to start with this one, just to kind of get it done. All right, so let's think then about what we're looking for. So I'll just kind of lay out. I'll start at the end actually, and we're going to work our way back, right? So what do we want at the end? We're going to want to print the top n similar movies. Okay, so that's what we want. Because or here are the shoes. You know, if I recommended Adidas, I like Adidas, let's say, then you need to what other people are buying. If they buy Adidas, maybe they what do people buy additionally when they buy Adidas? What's okay, a tracksuit that's also Adidas, probably, right? So then recommend that. You know, that's your objective if you're, you know, a seller of products. So then we're gonna need some kind of a function, print similar movies, let's call it. Print similar movies. That's gonna take in what do we need here? Probably let's call it the similarity matrix. Probably need that. So obviously we'll need to compute that one. Then we also need some kind of a movie ID, right? If I just selected a one, you could, if I selected several, what you can do is just run this several times, okay? And then find the most similar, and then from that bunch, find the ones that match, and then recommend the top ones, you know, something like that. So the movie ID, it's kind of like what I picked as my favorite movie. Say the Matrix is my favorite movie of all time. Then similarity matrix should take the matrix, the idea of it, and look for it in the similarity matrix. Just find the closest ones to it. Okay, so let's just leave it there for now. We might need other things. Obviously, we need the dictionaries because, you know, we'll have the reference and we'll need the real, etc. So we'll need to play with that. Okay, so if we have that, then the next thing we need is a way to calculate. So we need a way to calculate the similarity matrix. So we need a way to calculate this similarity matrix. Okay, so there's actually a function called the cosine similarity. You know, it's like, you know, cosine, right? Like algebra and trigonometry. So it comes from that. So if you remember sines and cosines. So there's some functions out there. We're just going to use it. But it or it's like the Euclidean distance. You could literally use the Euclidean distance. I'm not, you know, in fact, try it, right? Try it if you want to compute these. But, you know, it's been shown that the cosine, it calculates like an angle between the data. And by doing that, in terms of similarity, it's a little bit more accurate. Okay, so that's all it is. But ultimately, it's like calculating a distance function. So then we need to define a function for this. So we're going to call it top cosine similarity. Okay. And then, so here then, now we need we're gonna need now the other thing that we need actually is if we go back here, if you remember, we don't want to do the we want to just slice. We want to slice just, let's say 10, right? This is kind of arbitrary for me right now, but we're going to slice out that matrix because that we're only going to compute it because we just want a smaller space. Remember this? We just want a smaller space. So then we're going to need to slice that out. So when we do the cosine, it's going to be actually on the sliced matrix. So then we need sliced matrix. Okay. So we're going to need sliced matrix, and that's going to be, it's going to come from either U or V. You have to kind of play with that, right? Depending on what you're doing. But U is probably the one that contained the movies, I think. Yeah. So just double check. Okay, so then U, and then we're going to do slice it, right? So all here. And then all to, instead of saying 10, let's just say K, because maybe you would run this in a loop to find the optimal value. So let's say K equal, and you can start at 50, for instance, right? And so this is going to be 50 principal components, which are the first ones, right? You remember what this is, correct? So if I go back here, so these 10, right? So now it's 50. So you're slicing out in this direction 50. Okay, so now go back to the code. So that's the logic there. So then we need to specify, this is the similarity matrix. We have the slice matrix here. What else do we need? You probably need the movie that you want to show or view, right? Oh yeah, movie ID. So movie ID, this would be the movie that I pick, the matrix. I'm going to make up a number. E.g. the matrix. Okay, that's the movie. So you're going to, in print similar movies, you're going to just look for this movie in the similarity matrix. And then it should return or print. I guess it's called print, so you can print it out. What are the recommended movies? Okay. The similarity matrix, obviously we need to define the code for these two functions. They're actually our functions. They're not, or I'm not using like built-in functions, so we'll need to define those. It takes slice matrix, and then it's going to compute the similarities. So that's the part where you do, as I said, where you do this, right? Movies to movies. Okay, so we have that part set up. Okay. And then we're going to print them out. So let's now kind of focus. So now we need to define these functions. Okay, so we need to define these functions. So let's do. All right, so now we need to define both of those. So define, print, similar. What is it? Movies. Okay. So in here, this will return, or it'll print. So let's just put a print statement in here. And then the other one will be define top cosine similarity. Okay, and then let's just put a print in there. Okay, so print similar movies takes movie ID, and it also takes the similarity matrix. And then top cosine similarity takes the sliced matrix. You guys see that? Making sense? So now let's, I guess, print similar movies might be the easier function to consider. So it's a function to print top n similar movies. Function to print top n similar movies. Okay. So let's see. So print, got the matrix, and I've got the movie IDs. Okay, so actually, what we're gonna do, instead of giving it the whole similarity matrix, we're just gonna give it the top indices here. So we're gonna just do all of that. So I'm gonna change this to top indices. Okay, so then now, if it's top indices, all we have to do is a for loop for I in top indices, right? And now we can just print. Print. We'll need here the movies. So the actual movies. So then we'll say actual movies I. Got it? So we're just going to look, we're going to have here already the top indices. So we really just need to print from the movie data the actual movie. And this might be like movies dot title. Okay. So actual movies I, print the title. So that's actually pretty straightforward. You can also print the actual movie ID that you had, and then from actual IDs, you print the top IDs. Do you guys understand this part? So because the really important thing is to get the top indices. So here, if I have 9,740 movies by ID, right, I'll have already the top indices 7, 13, 55, 80. Those were the top 20. So then I just look for those movies and print it out. Okay, so that should be taken care of. Then that means, though, that top cosine similarity is actually, this should be top indices. Okay, the most similar indices that we have here. So that's what top cosine should give you, and then it goes here. Okay. So we're gonna have, this will require a little bit more thinking. Top cosine similarity. This is a function. To calculate cosine similarity. And then it sorts by most similar and returns the top. You guys see that? So that's the logic that we need to implement here. Okay, so it takes the slice matrix. It should also take how many we need, the top n, so we'll need to specify that. Top n equal, this is different from the k, right? So this is different from, where was that? This is different from K50. This was the number of principal components to represent the movie in the space. Once we've done that, now we just want to say how many movies we want to recommend. So that's top n. And in this case, we can say that top n could be equal to 10, right? To recommend however many movies we want to recommend. So in top cosine similarity, we also specify top n. Okay. So now that we have this, and we want the top n to a specific movie, so we also need to specify the movie ID here. Which means this also needs the movie ID. Okay. All right, so now what remains is we have the movie ID. Okay, so this part, this is the cosine part. This is a little bit tricky, so let's just, let's kind of go with it. So here, so just use this code as is. First, we're gonna get, so we have the data, right? The slice matrix. That's what we have there. So we'll need to use that. Actually, we can just call it here data to make it shorter. But just be aware that it is the slice data. Okay, so then we're gonna do we're gonna calculate a magnitude first, so magnitude. And this is going to be we're gonna use a special function in NumPy called the Eigen Sum, EIN sum. All right, so this will do the so this is that multiplication thing that I was talking about. So this is this part here. remember, where we have to multiply each vector of size 50 with each other, with the other vectors, and that will give us the distance, okay? So that's what I'm doing now is I'm going to generate a matrix that has all the distances, okay? So I'm not going to go through the mathematical proof of why that works, right? So I'll skip that part, but just basically we're going to use that function and just be aware that we're going to multiply the data and obtain this similarity matrix, okay? So I'm going to go ahead over here and just do Eigen Sum. And then it says, okay, so we specify here that IJ, comma IJ, I. So this is the format, right? So, sorry, this should be all in single quotes. Okay, and then now this will give us basically to compare all the indices and calculate the distances. Okay, and then we plug in the data times database. Okay, so now that we have that, we also calculate a square root. Okay, so np dot square root sqrt. Okay, and so that should do the set the magnitudes, and then to calculate the similarity, we're going to do np dot np dot something times data dot t divided by something index something, yeah, something index times magnitude. Okay. Now this something that we need an additional parameter, which is going to be the specific movie. Okay, so this is actually so this is actually just, it's not just, I realize this, it's not calculating the entire similarity. It's just calculating a bridge similarity of the specific movie to all the other movies. So I initially thought it was doing all movies to all movies, but actually it's only doing one movie to all movies. So I was wrong about that. So so then it's really just the movie row that we want. So I get it. So movie row here, right? So that's the movie row. We're gonna grab from data the specific movie row. So in this case, it'll be the index that we selected, right? That's that should be the movie ID. Yeah, so movie ID. Yep. Movie ID, and then all the other columns. So we're grabbing, so think about it. What we're doing here is in the code that I have on the Brightspace, it's actually not going to compute. It's actually not going to compute, for all movies to all movies. Instead, we just slice out one movie, the one that we are interested in, with the P to P50, let's say. And then now we're going to calculate the distance between this one and all the other movies. So it's not all to all, it's only one movie to all. Okay, does that make sense? Yeah. So I was wrong about that, so sorry. But yeah, so that's the approach. So let's go ahead here. And movie, so now movie row is data, movie ID. Okay, so we have data, movie ID, top 10. Okay, that's correct. Then we have the movie. Now the IDs start at 1 in the data set, not at 0. So we actually have to adjust for that. So the way that we do that is, let's create something called index. And index will just be movie ID minus 1. So that should do it. So then here, you can play with that, but here then this is no longer movie ID, it's actually index. Okay. So that's data index all. And then now we are going to do let me just comment this one out. Now we're going to do similarity, which is the dot product between movie row and the data. So that makes a little bit more sense. So movie row and the data. This T here is just it's called a transpose, so it's just a linear algebra thing to do the multiplication. But just think of it as this function np dot is comparing movie row to all the movies. Does that make sense? So here, logically speaking, actually, we've got the movie, and which, this is what, 1 by 50, right? This vector is 1 by 50. If we selected K to be 50, so this is 1 by 50. And then here, this is, the movie row is 1 by 50. This is going to be 9,740 by 50, right? So we are now comparing movie row to all the movies in this thing here. And so I can take that out for now, just to simplify it. And then the last step then should be the arg sort. So now I'm going to do sort indices, which will be numpy arg sort and for similarity, right? So now I have, for that particular movie and all the other movies, I have distances. So now I'm going to sort that, right? Arg sort by definition should return the indices and not the values. So this should return returns indices of most similar or of smallest values. Right? No, it returns the indices, but sorted from the smallest to the biggest, right? So that's basically what it should do. So returns indices sorted from smallest to the biggest. Okay, so those are basically the 3 steps. And then once you have the sorted indices, that's what you return. So you're going to do print sorted indices. But you only return from beginning to top end, right? So the top, because they're sorted already from shortest distance to longest distance. And then top end is one of your parameters, which is the 10 top movies. So this should be the basic skeleton for this. So if you think about it again, if we repeat, this is the data, right? This is the whole data, right? So 9,000 by 50, right? The 50 principal components, there's 97,000, 92,000 movies, something like that. We've got the movie that we want to compare to, and then we want 10. We just do this to adjust the indices because they start at 1 instead of 0, right? I mean, you could have done this outside also and just pass the correct ID. Then you do from this, oh, I forgot to finish this one. So the movie row should be for that specific movie, all 50 components. You see that? I've got 1 by 50 here. And then here, disregard this part for now, because these are just like optimizations. But really, what needs to happen is you have a function that compares that specific movie row to all the data. So it's going to calculate the distances between them. And then once you have that similarity, you have basically the similarity between that movie and all 9,000 movies. Now you sort it, gives you the indices from shortest distance to longest distance. And then from there, you just select the top 10. Does this logic make sense, guys? Are there any questions about this so far? So again, so I'll repeat. So the logic is, if you think about it, go to the whiteboard. Okay, so think of it this way, right? These are the movies that we get from you. There were 9,740 by 9,740, let's say. But we slice this, well, actually the whole thing, and it becomes our sliced, which is 9,740 by 50, because we just selected the first 50 principal components. You see that? Remember, that's the logic, right? Then this is data, slice data. Then we have that we have one movie ID. So let's say 3,000. That's the movie that I like, the Matrix, right? And then what do? I take that, I need to slice out this row with all 50 components. That's this part. Here, I did that. I sliced it. Index, all. So 3,000 by 50. Then I need to calculate the similarity between it. So that's this movie row, that whole vector is going to be compared to all the vectors. So now I have, if I go to another link over here, now I have all of them, 9,750 by 50. And then I slice this one out, let's say 3,000. So I have that one, which is just 1 by 50 also. That's the matrix. And then that dot function that you saw there is what's going to compare this vector to that vector, to that vector, and so on, to all of them. So that it returns what? It should return something that is 9,750 by 1 with distances in it. You guys see that now? So, because remember that this is a vector space of size 50, and then so this is equivalent to saying, you know, imagine this is R50. So we took our movie, and now we compare it to all the other movies, the 9,000 movies in there in that vector space of 50. This returns that vector 9,750 by 1. So the values might be 3, 5, 0, 1, 17, 800, right? Something like that. This might be 900. So that this vector here is actually, it's actually this one. Do you understand? That's what that should give us. And now I do an NPR sort of that to return the top indices. So now I'm going to do, if I think about it, this is 1, 2, well, I'm sorry, 0, 1, 2, 3, 4, 5, 6, right? So that NPR sort, if this is A, so returns what? Returns a list of these sorted. So how do you sort this? So it's actually sorted. It's 0, 1, 3, 5, 17, 800, 900, correct? That's the numbers sorted. But it doesn't return the numbers themselves. It returns the indices, right? Which is really what you care about because those are the movie IDs. So then that's going to be 0 is actually 3, 1 is actually 4. Oh, sorry. 0 is actually 3, 1 is 4. What was this number? 3, right? So 3 is actually 1, 5 is actually 2, 17 is actually 5, 800 is actually 6, 900 is actually 0. You see that? So this is what you get. The list of indices. If I just take the top 5, oops. If I just take the top 5, just those. So then now I know that for the matrix, I just need to look at ID 3, 4, 1, 2, and 5. And those are the movies that I want to write. That's it. Everything else that we're going to do to this code is just improvements like optimizations. But this is the basic logic. So just let's stop here. Think about this, okay? Think about this logic, play with the code a little bit, but that should be the, in essence, the steps of this. Did you guys understand the basic steps? So again, grab the movie, compare it to all the other movies. That gives you distances, sort them, get the indices. Questions? Yeah, go ahead. Well, run it. So now you have to pick a movie. So let's see. So you would have to give it some ID, movie ID 17. Indices. Okay. Yeah, so let's see. In print similar, top indices. Oh yeah, I see. Yeah, so we have, this has 3 is what it is. So actual movies is the array, movie IDs array, correct? I think that was the actual movie. Okay. Top indices. Well, so let's just comment this one out. Let's try top indices. See if that works. Okay, so that worked. So top indices, so we don't have to worry about print, but this did give us the top indices for a given ID. Do you guys see that? Now, the only thing that's important here is remember, we're currently not using the real IDs, we're using the reference IDs. So you're still going to have to go to the dictionary and look these up. Do you guys understand? So here, for instance, we've got in cosine, we selected movie 17. We have 50 components. We give it that. We give it the movie ID. We select the top 10. So then we go in here, select that movie, compare it to all the other movies, gives us the similarity. Then we have the arc sort. These are the sorted indices that we have. Okay, so now we just have to print. So the trick would be what? Which dictionary do we need? We ref to real, right? Movies ref to real. So ref to real. Okay, so we're gonna do movies. And then this is gonna be 17, right? And it should give us then the real one. Real my ID. You guys see that? And then for the other ones, we need to for ref in top indices, right? Top indices. And we need, again, ref to real, ref, and that will give us the real movie ID. You see that? And then now you need to go into the actual movies array. So which one had, so that's in movies, right? So that's in data movies here. And data movies, we need to find the actual movie name. So the actual title. But we haven't done, I guess we haven't done that part yet. So if I run these, print real my ID, and here we're going to print real movie ID. Okay, so I'm going to run that. What is in top indices? It didn't return anything? Okay. Yeah, so that's the problem. It didn't return. Where? Oh, did I not do that? Okay. Yeah, okay, that's a good catch. Thank you. Okay, so now it's not a none, right? Ah, there we go. You see that? So that's basically the. So that should be how many top indices? Oh, yeah. So it's gotta be top n, right? Okay. There we go. That's the code. Right there. Now you have to look for these movies in the actual text file that has the matrix, and then you have to, so if it's a matrix here, then these should be sci-fi movies, and you'll know it works. If you try romance, it should be romance movies. Do you guys understand? This is clear enough. So we'll continue with this on after the exam. All right, so I'm not assigning the homework yet. You just have to study for the exam. If you want to look at the finished code, it's on GitHub, so just get it from there. It's got all the details. Or look at this video and just basically I would recommend from here, you look up these movies in the movies matrix. That will have the ID to the movie itself. And then just corroborate if it works. There's a few optimizations that we can do that would make it work even better, possibly, but just work through it. Any questions? So the code is on, as I said, it's on GitHub. So let's go over here. So the actual finished code with all the details should be on the GitHub under SVD recommender. So you can play with that. Script is basically the one that I was doing today. Or otherwise just finish it up here. But the last part for you to corroborate would be, as I said, if you pick a romantic movie, then these should be romantic. If you pick a sci-fi movie, these should be sci-fi. If you pick whatever, a comedy, these should be comedies. And then you'll get a sense for whether or not it's working. All right, think about it, and then we'll pick up exactly here on Thursday and finish up the script. And then after that, once we have this working, I'll assign it as a homework. Any questions? All right, so let's stop here for today, and I will see you guys on, well, the exam will be on Monday, so no class. You can just take it online, and then we'll meet again on Wednesday. Okay, sounds good? All right, good.